Welcome back. Last time we paid off a long-standing debt and proved that e to the x is its own derivative. Along the way, we snuck in one tiny use of a technique we hadn't formalized yet, implicit differentiation, to get the derivative of the natural log of x in a single line. Today we promote that technique from supporting role to lead actor. Some curves in the plane are not functions. The circle x squared plus y squared equals 25 is the obvious example. The top half is a function of x, the bottom half is another function of x, and the whole curve fails the vertical line test. And yet the circle has a perfectly definite tangent line at every point, and we'd like the slope. Implicit differentiation gets it without ever splitting into half circles, without ever solving for y. Then we'll use the same idea in time. If two geometric quantities are related and both depend on t, the chain rule gives us one rate from the other. That's the whole content of related rates: ladder sliding down a wall, balloon inflating, a 5-step recipe, 2 worked examples, and 1 pitfall. Let's go. Here is the setup. The circle of radius 5, centered at the origin, has equation x squared plus y squared equals 25. This curve is not the graph of a function. A vertical line at, say, x equals 3 meets the circle twice, at the point 3, 4 on top and 3, -4 on the bottom. So when we write y as a function of x, we have to split into two pieces. The top half is y equals positive square root of 25 minus x squared. The bottom half is y equals negative square root of 25 minus x squared. To talk about the whole circle, we need both. Suppose we want the slope of the tangent line at the point 3, 4, which lives on the top half. We could go brute force. Take the derivative of the square root expression, plug in x equals 3, simplify. It works, but the algebra is fiddly, and the technique is hopeless for curves where solving for y is impossible, so let's not do that. There is a much better way. Here is the move. Treat y as some unknown function of x. We don't know the formula, we don't need the formula, and just differentiate the equation, term by term with respect to x. The equation x squared plus y squared equals 25 holds for every point on the circle. So whatever y is as a function of x, the two sides remain equal as x moves. Differentiate both sides. Derivative of x squared with respect to x is 2x, standard power rule. Derivative of 25 with respect to x is 0, it's a constant. The interesting term is y squared. Here's where the chain rule earns its keep. We're differentiating y squared with respect to x, but y depends on x. So think of y squared as the composition, outer is square, inner is y as a function of x, outer derivative 2y, inner derivative, the derivative of y with respect to x. Multiply, the derivative of y squared with respect to x is 2y times the derivative of y with respect to x. Every y term we differentiate picks up a factor of the derivative of y with respect to x, that is the entire technique. Assemble. 2x plus 2y times the derivative of y with respect to x equals 0. That's an algebraic equation with the derivative of y with respect to x in it, and we just solve. Subtract 2x from both sides, divide by 2y. The slope is minus x over y, that's it. One formula for every point on the circle. At the point 3, 4, plug in minus 3 over 4. The tangent line at 3, 4 has slope minus 3/4. At the point on the bottom, 3, -4, the same formula gives minus 3 over -4, which is positive 3/4, and that's right, by symmetry, the bottom half tangent has the opposite sign. Look at the structure of the answer. The derivative of y with respect to x equals minus x over y. The radius vector from the origin to the point x, y has slope y over x. The tangent has slope minus x over y. The product of those two slopes is minus 1. Tangent perpendicular to radius. Exactly the geometric fact you knew about circles since middle school, now falling out of calculus in 3 lines. Picture. The blue circle is x squared plus y squared equals 25. The dashed line from the origin to 3, 4 is the radius vector, with slope 4 over 3. The solid red line touching the circle at 3, 4 is the tangent we just computed, with slope minus 3/4. Visually, the tangent meets the radius at a right angle, and arithmetically, 4 over 3 times minus 3 over 4 equals minus 1, the perpendicularity condition. Implicit differentiation gave us the slope at every point of this curve with one short calculation, and at this specific point the slope is minus 3/4. The whole geometry of the circle, every tangent line, everywhere, encoded in the 4-character formula, the derivative of y with respect to x equals minus x over y. Why is this legal? The logic is simple but worth pinning down. Suppose f of x and y equals some constant c. Our circle's equation is f of x, y equals x squared plus y squared, set equal to 25. This equation holds for every point on the curve, which means that if we restrict to a piece of the curve where y is a function of x, the composite f of x, y of x is the constant c for every x in some interval. Two functions that agree on a whole interval have the same derivative on that interval. Both are the zero function, for a constant. So differentiate both sides with respect to x and the equation remains true. The left side's derivative involves the derivative of y with respect to x wherever y appears, by the chain rule, and the right side is the derivative of a constant, which is 0. That's the whole justification. Implicit differentiation isn't a new rule, it's just the chain rule, applied to an equation that holds identically. Second example, just to drive the technique home, the equation y cubed plus xy equals 6. Try to solve this for y in closed form. You can't. It's a cubic in y with x-dependent coefficients, and while a formula exists, it's grotesque. With implicit differentiation, we don't care. Differentiate both sides with respect to x. The term y cubed, outer is cube, inner is y. Chain rule gives 3y squared times the derivative of y with respect to x. The term xy, product rule, since both x and y vary. Derivative of x is 1 times y plus x times the derivative of y, which is the derivative of y with respect to x. So the xy term contributes y plus x times the derivative of y with respect to x. Right side, derivative of 6 is 0. Assemble. 3y squared times the derivative of y with respect to x plus x times the derivative of y with respect to x equals 0. Now isolate the derivative of y with respect to x. Factored out of the two terms that have it, quantity 3y squared plus x times the derivative of y with respect to x equals minus y. Divide. The slope is minus y over the quantity 3y squared plus x, one formula. Plug in any point that satisfies the original equation, and you get the tangent slope there. We never had to solve for y. Implicit differentiation is the warm-up. Related rates is the headline application. The shift is this. Instead of y depending on x, we have several geometric quantities. xy may be a volume, maybe an angle, and all of them depend on time t. They're related to each other by some geometric constraint, like the Pythagorean theorem or the formula for the volume of a sphere. Differentiate the constraint with respect to t, and every variable contributes its own rate. Every x picks up a derivative of x with respect to t. Every y picks up a derivative of y with respect to t. Every v picks up a derivative of v with respect to t. Mechanically, related rates is implicit differentiation with t as the independent variable. Conceptually, it's the chain rule that tells you how connected quantities respond when one of them moves. Let's see two examples. The classic. A 10-foot ladder leans against a vertical wall. The base of the ladder slides outward along the ground at a constant 1 foot per second, so the derivative of x with respect to t equals positive 1. The top of the ladder slides down the wall at some rate, the derivative of y with respect to t, which is negative because y is decreasing. The question, how fast is the top sliding down at the moment when the base is 6 feet from the wall? At that instant, by the Pythagorean theorem, the top is 8 feet up, 3, 4, 5 triangle, scaled. Picture the geometry. The wall is vertical, the ground is horizontal, the ladder is the hypotenuse of length 10. Let x be the horizontal distance from wall to base, and y the vertical distance from ground to top. Both x and y are changing with time as the ladder slides. They're not independent, they're locked together by the constraint that the ladder's length stays 10. The constraint is Pythagorean, x squared plus y squared equals 10 squared, which is 100. This equation holds at every moment in time, so we can differentiate it with respect to t. Left side, derivative of x squared with respect to t is 2x times the derivative of x with respect to t, by the chain rule, because x depends on t. Similarly, derivative of y squared with respect to t is 2y times the derivative of y with respect to t. Right side, derivative of 100 is 0. So 2x times the derivative of x with respect to t, plus 2y times the derivative of y with respect to t equals 0. The 2's cancel. Now solve for the unknown rate, the derivative of y with respect to t, it's minus x over y, times the derivative of x with respect to t. Now, and only now, plug in the numbers. At the instant of interest, x equals 6, y equals 8, and the derivative of x with respect to t equals 1 foot per second. Substitute. Minus 6 over 8 times 1. That simplifies to minus 3/4. The top of the ladder is descending at 3/4 of a foot per second when the base is 6 feet out. The negative sign is correct, y is shrinking. The magnitude, 3/4, is the speed. 5 steps. Memorize these and every related rates problem reduces to algebra. Step 1. Picture. Draw the geometry. Label every quantity that is changing with a letter, x, y, r, v, whatever, and every quantity that is constant with its actual number. The most common mistake at this stage is to label a varying quantity as a number, which destroys the problem before you start. Step 2. Relationship. Find an equation that ties the labeled variables together. It will come from the geometry. Pythagorean theorem, similar triangles, area of a circle, volume of a sphere, volume of a cone. Step 3. Differentiate both sides with respect to t. Every variable picks up its rate by the chain rule. Step 4. Plug in the numerical values of variables and known rates at the specific instant the problem asks about. Step 5. Solve for the unknown rate, and check that the sign makes physical sense. Positive for growing, negative for shrinking. Done. 2 examples in, and you'll see how the recipe runs itself. Here is the pitfall that catches almost every student the first time they meet related rates. In the latter problem, it's tempting to plug x equals 6 into the constraint first, get y equals 8, and then differentiate. Don't. Watch what happens. If you substitute x equals 6 and y equals 8 into x squared plus y squared equals 100, you get 36 plus 64 equals 100. True, but now all 3 quantities are constants. Differentiating both sides with respect to t gives 0 equals 0. True, useless. You destroyed all the rate information. Why? Because differentiation is a statement about what happens as variables change. If you've already frozen the variables at specific values, there is nothing left to change. The slogan, numbers are only valid at one instant, variables are valid for all time, and differentiation needs all time. So always, always, differentiate the constraint while everything is still a letter. Substitute numbers only after you've taken the derivative. This single rule prevents most related rates errors. Second example, a spherical balloon is being inflated. Air pumps in at a steady 100 cubic centimeters per second. So the derivative of v with respect to t equals 100. The question, how fast is the radius growing at the moment when the radius is 5 centimeters? Step 1. Picture a sphere of radius r with r increasing and v increasing as time passes. Step 2. Relationship. The volume of a sphere is 4/3 pi times r cubed. That's our constraint. Both v and r are functions of time. Step 3. Differentiate. Differentiate both sides with respect to t. Left side, the derivative of v with respect to t. Right side, 4/3 pi is just a constant, pulled out. The derivative of r cubed with respect to t is, by the chain rule, 3r squared times the derivative of r with respect to t. The 3 cancels the 3 in the denominator. So the derivative of v with respect to t equals 4 pi r squared times the derivative of r with respect to t. That's the rate equation. Step 4 and 5. Plug in and solve. Isolate the derivative of r with respect to t. It's the derivative of v with respect to t divided by 4 pi r squared. Substitute the numbers at the instant of interest. The derivative of v with respect to t is 100, r is 5. Denominator, 4 pi times 25, which is 100 pi. Numerator, 100. The hundreds cancel. The answer is 1 over pi centimeters per second. Beautiful number, and look at the geometric meaning of the formula one more time. 4 pi r squared is the surface area of the sphere. The rate equation says, volume growth rate equals surface area times radial expansion speed. Imagine the balloon surface as a thin shell. In a tiny time, dt, the shell moves outward by dr, sweeping out a volume equal to surface area times thickness, surface area times dr. Divide by dt, and there it is. The chain rule, geometry, and physical intuition all saying the same thing in 3 different languages. One last observation, as the balloon gets bigger, the derivative of r with respect to t shrinks like 1 over r squared, even though we're pumping at a constant volume rate. Big balloon, slow growth. A spherical surface area grows as the square of radius, so the same volumetric input spreads thinner and thinner. Why implicit differentiation and related rates are everywhere. First, most curves in real applications are defined implicitly and resist algebra. Level curves of functions of 2 variables, contour lines on a map, the van der Waals equation of state in thermodynamics, the orbit equations of celestial mechanics. None of these come to you with y on one side and x stuff on the other. Implicit differentiation is the only way to discuss their tangents and slopes. Second, classical mechanics with constraints. A bead sliding on a wire, a pendulum on a string, a rigid body with hinges, all are described by implicit constraint equations, and the dynamics use Lagrange multipliers, which are implicit differentiation with extra dimensions. Third, related rates show up wherever quantities covary. Fluid dynamics, gas expansion, chemical reaction kinetics, biological population coupling, GPS triangulation, radar tracking, machine learning gradient descent, all rate equations derive from constraints, all chain rule in time. And fourth, the deep theorem behind everything today is called the implicit function theorem. It says, if f of x and y equals a constant, and the partial derivative of f with respect to y is non-zero at a point, then y is locally a smooth function of x near that point, and the slope, the derivative of y with respect to x, equals minus the partial of f with respect to x over the partial of f with respect to y. You'll meet that theorem properly in multivariable calculus. Today's technique is its one-dimensional shadow. Where we landed. Implicit differentiation, treat y as an unknown function of x, differentiate the equation term by term, and let every y pick up a derivative of y with respect to x from the chain rule. The circle x squared plus y squared equals 25 gave the formula the derivative of y with respect to x equals minus x over y1, one formula for the slope at every point, with tangent perpendicular to radius falling out for free. The technique is legal because two functions that agree on an interval have equal derivatives there. Implicit differentiation is just the chain rule applied to an identity. Then related rates, the same technique with time as the independent variable. Every geometric quantity becomes a function of t, and every term picks up its own rate. The ladder problem. 10-foot ladder, base moving out at 1 foot per second, top descending at 3/4 of a foot per second when the base is 6 feet out. The balloon problem. Air pumped in at 100 cubic centimeters per second, radius growing at 1 over pi centimeters per second when the radius is 5. Both fall out of the 5-step recipe: picture, relationship, differentiate, plug, solve. And the one pitfall, differentiate before you substitute, never the other way, or all the rate information collapses to 0 equals 0. Next time, linear approximation and differentials. The tangent line as the world's simplest and most useful estimator. Newton's method, error propagation, the entire science of approximate computation starts there. The notation d, y equals f prime of x times dx finally gets a literal meaning. See you in episode 10. Related rates are calculus and time. One quantity moves, and the rest of the world responds. The same is true here. One viewer shares this video, and the channel's rate of growth changes before the day is out. Thanks for being one of the variables. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.